Great. Okay, so okay, now we are going to maybe not be talking much about mathematics for a while, just about hopefully simple ideas. So, okay, something I mentioned previously is how many bits or zeros and ones, what is the optimal way to losslessly compress a variable x. So to losslessly compress, meaning that you compress without removing information. And as I kind of said, the answer to this question is the entropy of the variable x. Um, so that question so the answer to this question is for a random variable x. But what happens if we change the question and there is no random variable anymore? Then the answer will not be the entropy, the answer will change. So let's uh, be more precise about what we mean. So uh, a function, an encoder, um, I call it a compressor, but it's like the encoder we had before, is a function which maps a realization x to a finite sequence of zeros and ones, or to, with a bijection, you could say it maps it to an integer. For example, the message m or the variable m that I presented before. So you just take something and you map it to zeros and ones. That's what a compressor is, or an encoder. And then you can look at the length of the string of zeros and ones, of the sequence of zeros and ones. And in what I presented previously, the length was n multiplied by r, as I kind of said. But anyway, so you can take the length of this sequence of zeros and ones, and then there is this theorem that says that uh, it's always possible to find a suitable compressor C such that you get the smallest possible length of the file, if you will, or the sequence of zeros and ones. The smallest possible length can be achieved by some compressor C, and the smallest possible length is between the entropy of x and the entropy of x plus 1. So the reason why this is different from the previous theorem that I showed before, because before we had an equality, we knew exactly what is the minimum number of, like the optimal value of r. But that was because we had an ergodic sequence or an i.i.d sequence. So it made things very easy because we could have a sum of i.i.d numbers, we could have law of large numbers, we could have concentration inequalities, so we can be very precise, and we got a very precise result. But this theorem actually, what's interesting is that it works for any random variable x. It doesn't have to be a sequence. You just take one variable x, you want to compress it, so you want to put it into an encoder and then into a decoder. And you can, the best way to do that is using a number of bits, a number of zeros and ones between h of x and h of x plus 1. Okay, so yeah, just to clarify, like what I said is at the beginning, the answer to the question, how do we compress a variable without losing information? The answer is essentially the entropy of x number of bits, zeros and ones. But now, what if we don't have a variable, a random variable? So what if you just have some object x? How many bits are needed to describe this, to compress x without losing information? That's why I say describe, because you want to represent x in zeros and ones, but without losing any information. So I don't know if you've ever heard of this, but this is exactly what is called the Kolmogorov complexity. It's just how many bits do you need essentially to describe an object. So complexity of some object, for example, a sequence of zeros and ones or an image or anything that is discrete, is essentially, as I said, I'm not doing much mathematics here. We'll just be talking about intuition for now. Essentially, it's the smallest number of zeros and ones that you need to describe the object. Let's make it a bit more concrete. You have several possible sequences, for example, and you want to compress each of them, then you can expect that the first sequence will be easy to compress. It will be easy to describe. You don't need uh, many bits to be able to describe this sequence. You can describe that it's a 1 that is repeat, so the value 1, and then you can describe the length of the sequence. For example, I don't know, maybe it's 30 or whatever. So you could write 30 in binary representation, the binary decomposition of 30, and the value 1, and this will give you a very small description of this string. Anyway, what I mean is this string is very simple. The second string is also simple because it has this pattern 001, then 001, etc. So it's also going to be easy to describe, meaning it will not require a very long description. Even if you wanted to actually describe it with words, it would not take much. But here I'm talking about what if you want to describe it with bits. And the Kolmogorov complexity, as I said, is essentially the smallest number of bits you need to explain what is, or to describe precisely what is the object. And the last sequence, which doesn't have any patterns, that one is going to be very hard to compress. What I mean by very hard, I just mean that you essentially, it will be long to describe. It will belong to describe, so it will take a lot of bits to describe. Maybe it will take the same number of bits actually to describe it. You probably cannot compress it much. Other examples, this image is very easy to describe. You require a very small number of bits. If you compress this, you can compress it in a smart way to have a very small file. Kind of similar for the chessboard. It's very simple to describe. You need the first color on the top, and then the number of columns and number of rows, and that's it. You just need this little amount of information and maybe the size maybe of each cell. However, if you want to describe or compress a very complex image, then you need a long description. You need a lot of bits, a lot of zeros and ones to describe that. Okay, the Kolmogorov complexity of this will be large, the Kolmogorov complexity of the red image will be small. And one thing that is true, is a kind of lemma, is that if you take a compression algorithm, or think of it just as a function in an abstract sense, it could be just some, for example, the JPEG algorithm. If you take an algorithm, then whatever the image you're trying to compress, whether it's very large or not very large, or very simple or very complicated, then the number of bits that will be produced by the algorithm A. So when you take image I and you put it in algorithm A, you get some zeros and ones. The length of this sequence is called BA, number of bits. And what you have is that the Kolmogorov complexity is smaller than that, essentially, plus some constant. That's not very important. And so, oops, sorry. So yeah, so essentially just again about intuition, that's among all possible algorithms, essentially the best one will give you this number of bits, the smallest possible number of bits to compress the image. So So for example, for the red image, if you apply JPEG, maybe it's a bad idea. Maybe it will give you a large number of bits because it might not be smart, I mean, tailored to this specific, very simple images. But there is a description that is with this number of bits, which is pretty small. Okay, so yes, there is a link between random variable and not random variable. So if you just for every value of xn or a sequence xn of i.i.d symbols, if for every value of xn you look at the Kolmogorov complexity, so the number of bits you need to describe xn, the smallest possible number, essentially, and you take an expectation now over what the distribution of xn, then you get exactly what we had before, which is what I showed in the very first theorem, which is that you get entropy. As n goes to infinity, when n is very large, the smallest number of bits you need to compress xn without losing information is the entropy of distribution of x. So distribution of x is the distribution of x1, or the distribution of x2 is the same. So yeah, just to say that there is a link between smallest number of bits for a given object without randomness, without random variable, and the first problem that Shannon was looking at, which is smallest number of bits to compress a random variable. So okay, now maybe this was all very intuitive, I mean, like informal. So now maybe let's look at this formally. So there is a notion of language in computer science, essentially. So if you know the Python, it has an interpreter. That could be your language, if you will. So when you give it zeros and ones, it knows how to read it. It knows what the language is. It's a Python language. So you give a program as a file in a Python file with zeros and ones. You give it to the interpreter, and the interpreter will be able to understand what it's about and how to execute it, etc. So that's the idea of language, is that there is some machine or interpreter that can read that can understand the language. So yeah, so any programming language actually has some abstract interpreter. And this notion of interpreter that takes like a program in zeros and ones and understands it is like a computer, actually. That's what a computer does. It's an abstract notion of a computer is it takes a program like zeros and ones, and it executes the program and gives an output like the interpreter does. And just for intuition, there is a notion of good language, which is like any programming language we know. The language has to satisfy some requirements to be useful, so we call it a good language or Turing-complete language. So yeah, there might be some additional constraints. Maybe it's not very important here. But okay, so just all of that is just because I want to define properly the Kolmogorov complexity, so that's why I talked about this. So given a language L, the Kolmogorov complexity of a discrete object O, let's think about a sequence of zeros and ones or an image. So the Kolmogorov complexity of O under the language L is the length of the shortest program. Think about the shortest Python program that will lead to outputting exactly O. So exactly the object, so the image, for example, or the sequence of zeros and ones, whatever the O is. So you look at possible programs, computer programs, or more generally programs, that if you understand them with the language L, you would get you can be able to execute those programs and get an output. And you look at programs which outputs exactly O, and the smallest program or the shortest program, its length in zeros and ones. If the program is using zeros and ones, then the number of zeros and ones, length of the program, is what we call the Kolmogorov complexity. And now you might think, oh, so there is a Kolmogorov complexity for Python and a Kolmogorov complexity for whatever Java or any, like if you change the language, you change the definition. But actually, not really. And that's for all good languages, so for all Turing complete languages, L and L prime, you have different definitions of Kolmogorov complexity, so one for each language. But these essentially functions do not differ much. There is a constant c such that there is distance at most c between the values according to language L and according to language L prime. And why this is relevant is because the object O can be any like discrete object, so any image, for example, of any size, any values for the pixels and any size, especially. So there is an infinite number of possible values of O. So for very complex objects, like complex images, this will be very big. The Kolmogorov complexity will be very big. So the constant C will be essentially negligible. So that's why I think it's good to think that there is only one real definition of Kolmogorov complexity. I think that's a good intuition to have, even though there is this actually to be formal and precise, there are different definitions, but they are close to each other. Okay, and that's the first strength, I call it, of Kolmogorov complexity, that is invariant essentially to the choice of the language. And now we're going to talk about the second strength of Kolmogorov complexity is this new way of talking about visual quality or audio quality or perceptual quality in general that has been studied actually a long time ago. People had forgotten, or maybe some people didn't know about it. And recently someone, a researcher at Google had the idea that, oh, we can use this Kolmogorov complexity theory of quality and perceptual quality to be able to work on many problems, many engineering problems or mathematical problems, if you will. So, okay, I'm going to just now present, okay, what is this theory that has been developed a long time ago that we can use to change our problem, to change the definition of our problem, and then I will show you what is the new problem, a new formulation. So, okay, so a basic problem that's let's say a new question. The first Kolmogorov complexity is the answer to the question of how many bits, how many zeros and ones do you need to describe an object without losing information. And here now there's a new question, is how do you give a score for an object to say if it comes from distribution P or not? So if it comes from distribution P, if you're confident or you're sure that it comes from distribution P, you want to give a small error or small score. But if you think it's very weird, like it's a blurry image, for example, something that is unnatural or precisely that doesn't look like it comes from distribution P, then you want a high value of the score. There's actually a term for this, is out of distribution samples. If you think that a sample doesn't come from distribution P, is out of distribution, then you want to give a high score, a high error in some sense. So that's a new question, and maybe I can make it more precise on an example. So imagine you look at a sequence of length 10, so 10 zeros and ones. Here it's just 10 zeros. And now you wonder, does this look like it comes from the distribution Bernoulli 1/4? So i.i.d samples, i.i.d coin tosses with a coin that is a bit uneven, unfair. So does this sequence look like it comes from the distribution? So this is a question we're asking, and we want to give a score on this sequence. High score if it's bad, if it doesn't look like it comes from P, and low score if it comes from P. That's the question we want to answer. And so there is one attempt, is to say, oh, the likelihood, which actually just means the probability. So you can compute the probability according to P of having this output. Because we know the Bernoulli distribution is easy to, it's like 3/4 times 3/4 times, etc. So we can compute this probability. And then we can, so if we don't know the distribution, if it's a bit more complicated, then we might estimate a P hat is an estimate for that. But let's say that we have access to P and then we can compute the probability of having this output. Then one idea is, okay, I'm going to give a score based on the probability. If the probability of having all zeros is very large, or is maybe not very large, but at least is reasonably large, so it's very probable that this will be from distribution P. So can give it a small score or a small error. And if I find that the probability is very small, then I will say, okay, this is not probable, it probably does not come from distribution P. That's the kind of idea. I will make this more rigorous later, but I just want to give you the idea for now. So actually, this is a bad answer to the question of how to give a score. This is a bad way to give a score. Why? Because it is true that this sequence, among all the sequences of length 10, is actually the most probable sequence of length 10 according to P. Because you get 3/4 for 0, and if you had any 1 anywhere, you get 1/4 for the 1, so it would give something less probable. So this is the most probable sequence. But does it look realistic? Does it look like it comes from an i.i.d. distribution? It definitely doesn't look like it comes from an i.i.d. distribution. It looks like it comes from how to say this, a constant distribution, actually. So we can say that it doesn't look very realistic. So if I just give the probability or the log of the probability as a score, it doesn't really accurately answer the question of, does it look realistic or does it look like it comes from P? So that's why I said it's a bad idea to just look at the probability, or sometimes called likelihood. In fact, what we would expect is that there will be 1/4 of ones and 3/4 of zeros. That's what we would expect. That's realistic. In some sense, if you find 1/4 of ones and 3/4 of zeros, you're not going to be surprised. Well, if you find only zeros when you throw a coin, you will be very surprised. It's very, it looks unrealistic. Maybe there is a problem with the coin or something. So anyway, so this is the I'm being very informal here, but roughly this is the problem and why we cannot answer this question like that. So the better way to answer it is actually, there's some people just from engineering, they just said, oh, let's add a modification to the previous expression. So instead of just the probability or the log of the probability, they added, they removed, actually subtracted the number of bits to compress the image X with the PNG algorithm. It's another algorithm. And they just used this, and it turned out that it was actually a pretty good score. If you look at some examples, it looks like it's a good score. But actually, this has already been proved theoretically very rigorously in algorithmic information theory a long time ago, that actually Kolmogorov complexity is the right answer for this question, the best possible score. is what we saw before. So you take the probability, you take it into account, maybe you take the log, but you also add the information of, is the object X very hard to describe? It takes a long description, a large value of K of X. Or does the object X require only a small description? And so intuitively, if you come back to the example of zeros, this would have a very short description. It's very short to describe. And because of that, then this will make K of X very small. So minus K of X will be very high. So the score will be high, higher at least than before. So just intuitively, maybe we can see that it's important to take into account how simple or how complex the object is to be able to talk about whether it's realistic, whether it realistically comes from distribution P or not. So more formally, the theory says that we cannot just look at any like score function because the set of all possible score functions is too big, is too complicated. So we need to have some restrictions first. So this is the definition here for restrictions on the score function. So you consider distribution P on discrete objects. So just put all the objects in zeros and ones. So this is the set of finite sequences. 0, 1 star is finite sequences of zeros and ones of any length. So a p-test, or a score function, if you will, is a function delta that takes a sequence of zeros and ones, so an object, and gives a score, which is a real number. So far so good, nothing changed, but the restrictions now that we put is that it's kind of computable. So it can be done by a computer, by an algorithm, approximately at least. So it's not just any function that can be very weird and very complex. And it might sound like, oh, why are we imposing this? This sounds weird. Actually, this is algorithmic information theory. So we need to be talking about algorithms just because of the name. But also, this is very powerful because there are not many functions actually that are computable in some sense, let's say intuitively. And this will allow us to have many lemmas. It will allow us to prove a lot of things. You can have very interesting theorems because of this restriction, because you only look at kind of computable functions. And the second constraint is, I'm not exactly telling you what it is, but it's just something that, so that it makes sense. For example, if the function delta is allowed, then the function 2 times delta should not be allowed, because otherwise, if you just multiply by 2, the score is kind of the same function, essentially. It's not very interesting to look at any possible score, any possible multiple of a score. So there is some standardization constraint, so to make sure that we don't have this problem. And once we have that, then there is the optimal p-test, or the optimal score function. As I said before, very rigorously, the function that is defined like this, there is some constant here that I'm not mentioning, but essentially it is what I showed you before. This is the best possible score function in the sense of this property which is here above. And we call it the universal p-test, the universal test, or universal score function. So let's look at this property to understand why this property means that this delta 0 is the best score function. So the property says that for any test delta that you might, any function that is possible, that is satisfying the constraints I showed before, delta 0 will always be above delta up to some constant. So whatever the object x that you're considering, delta 0 will give a higher score than delta. So what this means is that if the score function delta gives a high score, so it says that x doesn't look realistic, it looks out of distribution, it doesn't look like it comes from P, So if it gives a high score, then automatically delta 0, we can be sure that it will give a high score as well. So in some sense, if some test delta or some score function delta is able to notice that there is something weird about object X, it doesn't look realistic. If delta is able to notice this, then delta 0 will also be able to notice this in some sense, because it will also give a high score if delta gives a high score. So in other words, delta 0 can notice everything. I'm exaggerating a little bit, but it's just to give you the intuition that anything that some delta can notice, some score function delta can notice, any irregularities, anything weird, delta 0 will also notice it. Up to this, maybe this constant C, let's say. So yeah, this is the property. And again, the reason that we are able to prove such a theorem, not me, but the people who did that a long time ago, the reason we are able to is because we only consider like a very small uh, class of functions that are essentially algorithms or close to being algorithms. That's why we get very good properties, very good lemmas, etc. So yeah, we have this specific property. So now we have this score function that is able to give a score for an object X to say whether it looks realistic or not. So whether it looks like it comes from distribution P or not. So of course we can apply this to our original problem, because we didn't want blurry images. We wanted like visually pleasing, visually, yeah, visually pleasing images. So now we can use this for our problem. And okay, so oh, um, I guess I've taken maybe more time than I thought I would, but I'll try to finish quickly. So this just to remind you the formulation that was before. So you have the distortion constraint, and you have this constraint that you want the distribution of the reconstruction Y to be close to the distribution of X, the original thing you want to compress. And now what we're going to do is change things a bit. So it's going to be nearly the same thing, but instead of looking at just one image, or sorry, one sequence xn that you want to compress, we're going to use the same encoder and decoder to compress several sequences. So we have several sequences from 1 to B to Bn. So all of them are like before, each of them is a sequence of length n. And then you have an encoder and decoder that you consider. And when you fix the encoder and decoder, now what you can do is you can put sequence number 1 in this, and you get a sequence y1. You can put now sequence number 2, you get y2. And so you get these couples of xk, yk. And now you want to judge this algorithm, this encoder and the decoder. Judge if they are good or not good. So what you're going to do is kind of like before. So just show you the expression before is the average of the distance between xt and yt. So x1, y1, x2, y2, all the symbols all the elements of the sequences. And now you just take the same expression, but you add an average over the batch. So an average over k. But it's the same expression, it's just you add the average over k. For the second part, now you take the score function that, as I said, that involves Kolmogorov complexity, for example, or maybe something else uh, that we saw before, and you use it to judge these objects. So actually, to be precise, you can take the concatenation. These are sequences of length n, then you can concatenate them to make a long sequence. And then you give this sequence to the score function, and it gives you a value. If it notices some irregularities, then it will give a high score. If it doesn't, then it will give a low score. And now, because we're looking at n going to infinity, um, I can't really explain this quickly, but let's say that this is a very good constraint to have. This is very rare that you find an encoder and decoder who satisfy this property. This makes essentially the score be very contained. It doesn't explode as n go to infinity, which is very rare. That means that these sequences y1 to yb are quite realistic, essentially. So anyway, this is the new problem that I've defined, that I've considered. And actually, it's very similar to the previous one. Why? Because if you just take very large B, so a very large number of samples, then you actually get this same constraint as before. So I can't show you the proof here, but you can, let's say, trust me on this, that this constraint is when you look at a finite number of samples from 1 to bn. But if bn is very, very large, then actually this constraint is going to be essentially the same as this constraint that we had before. So what this means is that the original problem is the same as the new problem when you look at a large batch, or like a large number of samples. And so what our theoretical results are, and I just have 3 slides left. So when the number of samples that you consider is not large, is reasonable, then deterministic encoder and decoder become optimal. So we don't have anymore this weird behavior that we had in the previous formulation where you need a randomization, which is very weird, or that you need a lot of common randomness, which it was also not possible in practice. And now with the new formulation, if you have a reasonable number of samples, then deterministic codes are optimal. And I say that despite that the critic delta or the score function that we consider can be a very good score function, like something involving Kolmogorov complexity. So even if you're really very strict about visual quality, you really want a good visual quality, you still will be able to achieve that only with deterministic codes. You don't need to add randomness to still be able to achieve that. And now just to finish, if the batch size of the number of samples is very, very large, essentially then as I said before, but this is a rigorous, let's say, form, that the problem, I call it the trade-off, but let's say the problem is exactly identical to the original problem. So the original problem is where there was a distance between probability distributions. We wanted the yn to have the same distribution as the original xn. And now I'm saying that my formulation is the same as before if bn is large, if the batch size is large. And just to explain kind of why we wanted to do this, we wanted our formalism to make more sense regarding practice, because it doesn't make sense. Okay, maybe I'll just explain this with the formalism here. So this constraint is actually very, very strict. And what my argument is that it is much more strict than what humans care about. So when a human is going to look at an image or a sequence, they're not going to be able to see small variations. If the distance is not zero, if the distance is not too big, then the human observer will probably not see the difference. This way of measuring realism or visual quality or perceptual quality is very, very fine and is much finer than what a human being is able to see. And what we essentially show is that if you give to a scoring function delta, which could be anything, could be a good scoring function, or it could be just be like a human, what a human would do, a simple um, computation. Then if you give a small number of samples, which is what actually happens in practice, then you don't need randomized cause, you don't need insane amount of common randomness. So if you define the realism constraint or visual quality constraint or whatever in a way that is practical, that is feasible in practice, that makes sense with respect to practice, by looking at only a small number and not an infinite number of samples, then you get something that essentially makes more sense, I would say, with respect to practice. While if you take this distance between probability distributions, then what you're actually doing theoretically is as if you give a very, very large number of samples to be tested and to be scored. But this never happens in practice. There is no human who is going to look at 3 million images to be able to determine if the algorithm is good or not good, if the um, it's sufficient to look at maybe 20 images to get a very good idea of whether the algorithm is good or not, whether there are blurry images, for example, or whatever. So yes, this is kind of the motivation why we wanted to do this. And yeah, thank you for your attention.